بسم الله الرحمن الرحيم. اليوم نبدأ محاضرتنا رقم 6 في الأوبتمايزيشن. محاضرة اليوم راح تتكلم عن بعض الأمور الخاصة في conditions for optimality. So our title today is necessary conditions for optimality. خلينا نتذكر احنا وياكم Taylor series. Recall Taylor series expansion. Taylor series عبارة عن expansion of a function around a certain point. So we'll assume this is fx of x star plus some delta x, which is equal to f at x star plus the gradient of f of x transpose at evaluated at x equals x star multiplied by delta x plus 1/2 delta x transpose Hessian of the function evaluated at x equals x star times delta x plus third order terms and so on. And here we have delta x is equal to this x minus x star. So the evaluation of x is this one, x star plus delta x equals to x. So delta x is equal to x minus x star. Okay, so we have third order, fourth order terms and so on. We'll stop here. Usually delta x is very small, so going to a first order derivative, second order derivative sometimes is enough, because delta x to the power third and fourth will be very small value. Okay, we will see the condition now on the first order conditions. First order conditions. Of course, first order conditions means the gradient here. Okay, if the norm of delta x is very small, this means that higher order terms of the Taylor series will be negligible. So we can approximate f of x star plus delta x to be equal or almost equal, approximately equal to f of x star plus the first order term, which is this one here. So this is the gradient transpose of f of x times delta x. And this one is evaluated at x equals x star. Okay, so it's the inner product of the gradient evaluated at x equals x stars times delta x. This is the inner product. Okay, now if x star is a candidate minimum point, this means that the function should go up or at least not go down if delta x is not 0. Yeah. So, and this is very clear, you know. If you have a delta x, then you have f of x star plus the inner product. Now, if this is a minimum, then this one should be positive, actually, so that any value different than x star should have a value greater than f of x at x star. Okay? So this means that the inner product of the gradient fx at x equals x star times delta x should be greater than or equal 0. Because we said here, at least not go down. So this one could be 0. So this one will be the same as this one, but it shouldn't be less than f of x star if x star is a candidate minimum. All right. However, if this term is positive, so the times delta x is greater than 0, then this would imply that f of x star minus delta x is equal or approximately equal to f of x star minus the gradient of f of x at x equals x star times delta x. So we introduce a minus delta x, so this is a minus. So this is supposed to be less than f of x star because this value is a positive value. Now if you have x but you go to the other direction, it's supposed to be with a minus sign. Anyway, x star is a candidate and it's a minimum point. So whether you go to the left or to the right, you have to have the f of x is the minimum, and no value of any x should go below f of x star. So this is a contradiction, actually, which means that So this is a contradiction. Since x star should be a minimum, point. This means that, so the only solution for this to be true is that, so this one is positive, this one is also negative. The only thing to accommodate for this is to have delta, or the gradient of f of x, evaluated at x equals x star times delta x should equal to 0. Okay? Positive, negative, and so for contradiction you have to have the gradient at x equals x star should equal to 0. So since this should be true for any delta x, we have the gradient of f of x at x equals x star should equal to 0. So this is our condition regarding the gradient or the first derivative. Okay? Therefore, the gradient must be 0 for a minimum point. Actually, this is a first order necessary but not sufficient condition for x star to be a local minimum point. Okay, let me just elaborate on this. Let's take a curve in the two-dimensional space and see that if you have like this a curve where you have a minimum here, so you have here your x star. Now, if you have the gradient here is just the slope, so this is your slope at this point. This is your slope at this point. So the slope here is positive slope, which means that you have positive gradient. And you have here is negative slope. Let's put it in the same manner, negative slope or negative gradient. Now if you move in this direction and you have x here, then you have delta x is equal to x minus x star, and this one is greater than 0. If you move to this direction, then you have x in this direction. So delta x is equal to x minus x star, and it's less than 0. So delta x here is negative. Delta x here is positive. So positive times positive is positive. Negative times negative is positive. So in all directions, when you go up, so delta, the inner product between delta x and the slope is always a positive value. The only value that you will have here is, you are moving with a negative slope, and then suddenly it changes to positive slope. At this point here, where you have the minimum, the slope is equal to 0. Slope equals 0 at x equals x star. Okay? Okay. So, any point or any points that satisfy the gradient of f of x at x equals x star equals 0 are called stationary points. They are called stationary points. Oh, by the way, as we mentioned here, or in the last statement, we mentioned in the last statement that was here, is that this is a necessary condition but not sufficient. One example for the necessary condition but not sufficient is to look at the f of x, which is equal to x cubed. And x cubed here, the derivative, your stationary point, you have stationary point at x equals 0. So x star equals 0. And this one is a deflection point. Actually, it's not a minimum. You have values below, values above. But if you do the gradient, which is f prime of x equals 3x squared equals 0, then x star equals 0. So, and this is a deflection point. This is why we call it a necessary condition but not sufficient. This is why you have to go one further step. When you find stationary points, does not mean that it could be a maximum, it could be a minimum, and it could be something else, like here. So it's a deflection point. It's not the minimum. It's neither minimum nor maximum. Okay. So we have to go one step further and go with the second order conditions. Okay? So we discussed here the gradient. So the second order conditions, we will go for the Hessian matrix. So we go more in the Taylor series expansion once again, and we will assume that we have a stationary point x star, since the gradient of f of x is 0 at all stationary points, the Taylor series expansion will be f of x star plus delta x is approximately equal to f of x star plus the second order term, which is 1/2 delta x transpose the Hessian matrix, which is the del squared of f of x evaluated at x equals x star times delta x. Okay? The gradient term is equal to 0 because we are evaluating the gradient at x equals x star, and the gradient at x equals x star is equal to 0 at all stationary points. Okay. Okay, of course, this approximation is true assuming that the norm of delta x is very small. Okay, so this approximation is true assuming that the norm of delta x is very small. Okay? So, for a strong minimum, for a minimum to have, we have to have that this one here, this term. If this term is greater than 0, then this means that if any value of x which is different than x star will be greater than f of x star. So strong minimum will exist at x star if delta x transpose del squared of f of x at x equals x star times delta x is greater than 0. So if this product is greater than 0, then this one is a minimum. Okay, so for this to be true, for arbitrary delta x not equal to 0 requires that the Hessian matrix be positive definite. Matrix. Okay, it should be positive definite matrix. Okay, now I think, I don't know if you know this term before, but let me just elaborate on this. What is positive definite matrix. When we call a matrix is a positive definite. Okay, as a definition, a matrix A is positive definite if Z transpose AZ is greater than 0 for any vector Z not equal to 0. So for any arbitrary vector Z, if you have Z transpose A times Z greater than 0, then the matrix is called positive definite. Okay? You can pick it positive Z, negative Z, as long as Z does not equal to 0, and you multiply this, you get it greater than 0, then the matrix is positive definite. We will see in a while how can we check for the positive definiteness of a matrix in a more easy way. But before that, let me just continue the explanation about the positive definiteness. A matrix A is positive semi-definite if Z transpose A Z greater than or equal 0 for any vector Z. So for a matrix to be positive definite, this should be greater than 0. For positive semi-definite, this should be greater than or equal to 0. Okay? Now, there is an easy way to check for the positive definiteness by looking at the eigenvalues of the matrix A. So we can check these conditions by testing the eigenvalues of the matrix. If all eigenvalues are positive, then the matrix is positive definite. If all eigenvalues are non-negative, then the matrix is positive semi-definite or semi-definite. Okay? Okay. So, to make use of those two ideas here, then a sufficient condition for X star to be a strong minimum point of f of x are the gradient of f of x at x equals x star is equal to 0, and the Hessian of f of x at x equals x star is positive definite. Positive definite matrix. On the other hand, necessary condition for x star to be a minimum strong or weak of f of x are the gradient of f of x at x equals x star equals 0, and the Hessian of f of x at x equals x star is positive semi-definite. So positive semi-definite is a necessary condition. Positive definite is a sufficient condition. Okay. Let's see this through an example. Let's see how can we discuss the optimality, looking at the all those points that are stationary points, and see how we can calculate the minimum and discuss it together. Okay. Let's take an example. Before this, let me just introduce the subject a little bit, and we will call it the Eigen system of the Hessian. So the Eigen system of the Hessian, and we'll do this through an example. So we'll do consider f of x equals to x1 squared plus x1 x2 plus x2 squared. Okay. We want to discuss find the stationary points and see whether this is a minimum or not. So we'll do the gradient of f of x, which is equal to partial f of x, partial x, 1, and partial f of x, partial x2. And this is equals to 2x1 plus x2, and the other one is x1 plus 2x2. So if we say that this is equal to 0 to find the stationary points, so you have 2x1 plus x2 equals 0, and you have x1 plus 2x2 equals 0. If you multiply by minus 2 and add together, then those will be cancelled, and you have here minus 3x2 equals 0, x2 equals 0, and x1 equals to 2 minus 2x2, which is equal to 0. So our stationary point will be so our x star here is equal to 0 and 0. So this is our x star. Okay, let's find the Hessian matrix, which is equal to partial f of x, partial x1, partial 2, partial x1 squared, partial 2f of x, partial x1, partial x2, and this one here is partial 2f of x, partial x2, partial x1, and the last one is partial 2f of x, partial x2 squared. So if you apply this to the first derivative, which is the gradient, then the second derivative here is 2, and here is 1, and here is 1, here is 2. So this is our Hessian matrix. It's a constant, does not have values inside. And looking at this, we cannot say that this one is positive definite, positive semi-definite, negative definite. We cannot conclude until we find the eigenvalues of this matrix. And to find the eigenvalues of a matrix, to find the eigenvalues of a matrix A, we have to find the determinant of lambda I minus A, and we equate it equal to 0. Those brackets here are the determinant of the matrix. So lambda I minus A here, we need to find lambda I minus the gradient square of f of x, which is equal to the determinant of lambda minus 2, minus 1, minus 1, and lambda minus 2. So the determinant will be lambda minus 2 times lambda minus 2, which is lambda minus 2 squared, minus 1 times minus 1, which is minus 1. And we have to equate this equals to 0. So this is equals to lambda squared minus 4 lambda plus 4 minus 1 equals 0. So you have lambda squared minus 4 lambda plus 3 equals 0. And we can say that this is lambda 3, 1 minus minus equals 0. So you have lambda 1 equals 1 and lambda 2 equals 3. So we have two lambdas. Both are positive. And this means that our so positive definite, and x equals is a minimum. Okay? Okay. Okay. So as a practice, you have f of x equals to minus 1/4 x1 squared minus 3/2 x1 x2 minus 1/4 x2 squared. Find the stationary point or points and evaluate the Hessian at the stationary points and decide on those points if they are minimum or not. Okay. Notice here if some of the eigenvalues are positive and the others are negative, then we have what we call a saddle point. Okay, so to see this in this example, plot the 3D surface of f of x and plot the contour lines of f of x. Okay, please do this exercise and examine this function, see the stationary points, evaluate the stationary points, the Hessian at the stationary point. You will find out that some of the eigenvalues are positive, some of them are negative, so we will have a saddle point and plot the 3D, see how the saddle point is in 3D figures, and examine the contour lines and see what will happen. Okay? Enough for this for today. Thank you very much, and we will continue next time.